Welcome to another episode of Classes with Atish. Today our topic is collisions, and this is an extension of the concept of conservation of linear momentum that we just discussed in a previous video. So let's talk about collisions in detail. Okay. When two bodies that are moving with a uniform velocity, they collide with each other, then that is called a collision. A collision can be multiple types. So let's define that first. So we could have something called elastic collision, or we could have inelastic collision, and we could actually have something in between which is called partially elastic or partially inelastic collision. Okay. Now there are different phases of collision, so let's talk about that as well because that's important. So when two bodies, let's say body 1 and body 2, they are moving, okay, this one is moving with u1, this one is moving with u2, so that u1 is greater than u2, so only then they will catch up, right? And at some point u1 will collide with u2. So this first phase, when it is approaching body 2, this is called approach. Okay. The second phase is when body 1 and body 2, they have touched and maybe they have gone a little bit ahead and they have deformed each other. Okay. So this phase is called collision or deformation. Okay. And then after collision, body 1 moves with some final velocity v1 and body 2 moves away with some final velocity v2. This is called separation phase. Okay. So there are three phases: approach, collision and separation. Okay. How do we differentiate between elastic and inelastic collision? What is different? So first up, momentum or linear momentum, that is conserved in all of these, elastic, inelastic or partially elastic. It is always conserved in all of these collisions. Okay. So which means what? Because there is no external force here, there is some interaction here, but one exerts a force on 2 and 2 exerts an equal and opposite force on 1. So for the system 1 and 2, those are internal forces, they cancel out. There is no external force happening during any phase of collision. So because there is no external force, momentum is always conserved in elastic, inelastic or partially elastic collisions. Second thing is kinetic energy. So for elastic collisions, kinetic energy is conserved. Okay. So which means what? Whatever total kinetic energy of the system, which is body 1 and body 2 together as a system, whatever kinetic energy was there at before collision, after collision, during separation as well, the total kinetic energy remains the same. Okay. Okay. What about inelastic collision? Does kinetic energy remain the same at approach and at separation? No. So that is the difference. So there is some loss of energy that happens because with kinetic energy, total kinetic energy of the system reduces, and that loss of energy is because of this deformation which is not regained back in inelastic collision. Okay. In perfectly inelastic collision, these two bodies, they stick together. In partially inelastic collision, they don't stick together, but then they are permanently deformed. However, in elastic collision, although at collision there is some deformation, but after that collision is complete, there is some negative work done, and both the bodies, they regain their shape. So net work done is zero. So that's the reason kinetic energy is conserved before collision and after collision, okay, in elastic collisions. For partially elastic collisions also kinetic energy is therefore not conserved, okay. Okay, so you understood the difference between elastic, inelastic and partially elastic collisions. So between these two, inelastic collisions or perfectly inelastic collisions, the bodies stick to each other. Okay. In partially elastic bodies, the bodies don't stick to each other but permanently deformed. So there was some loss of kinetic energy, okay. All right. One important consideration when we look at both conservation of momentum and conservation of kinetic energy in elastic collisions, and basically conservation of momentum in all the three types of collisions, is this. Momentum is conserved all the time. Let me write that down. Momentum is conserved throughout the collision phases. So momentum is same during approach, during collision, during separation. However, for elastic collisions or perfect elastic collisions, kinetic energy is only conserved before and after collision. During this collision, there is a drop in kinetic energy, okay. For inelastic and partially elastic collisions, kinetic energy is not conserved. Kinetic energy is not conserved. Okay. Now let us look at this a little bit more deeper. So if I plot momentum and time, okay, and if I plot kinetic energy and time, and same thing if I plot kinetic energy and time for inelastic, for elastic collisions, and momentum for elastic collisions, okay. How would this look? Momentum is conserved throughout, so this will be always a straight line. So let's say this is at collision, this is before, this is after, okay. For perfectly elastic collisions, kinetic energy before and after are conserved, but something happens at collision. At collision, there is a sharp drop of kinetic energy and then it is conserved. So you can equate kinetic energy at approach phase with kinetic energy at separation phase, but not at the collision phase. For inelastic or partially elastic collisions, kinetic energy is not conserved. So which means, so let's say this is at collision. So there was some kinetic energy before collision. There is a drop and there is a drop in kinetic energy. Maybe not that significant, but there is a drop, okay. So hope you understand this difference, because it is critical to understand the theory behind each of these phases of collisions for elastic, inelastic and partially elastic collisions, okay. Now let's look at some of the math behind elastic and inelastic collisions. One other thing I do want to mention, Momentum conservation, this is applicable for all collisions. All types of collisions. Okay. Okay. Now let's talk about elastic collisions. Okay. So again, to just restate, in elastic collision, linear momentum is conserved and kinetic energy between the initial and the final states are conserved. So during approach, whatever the kinetic energy was there of the system, during separation, the same kinetic energy of the system will be there. Okay. So now let's say there is one body 1 which is moving with u1, and then there is another body which is moving with u2, u1 being more than u2. Okay, they collide. So they undergo an head-on elastic collision. Okay, head-on elastic collision. What does head-on elastic collision mean? Head-on elastic collision means their line of impact is same as their line of motion. So it is happening at the same line, so there is no oblique collision. So whatever the change in velocity will happen, it will all happen in the same line. Okay, so it undergoes an head-on elastic collision. After collision, body 1 has a velocity v1 and body 2 has a velocity v2. Okay, it's also given mass of this one is m1, this is m2, m1, m2. Okay. So let's apply the definition of elastic collision. So linear momentum is conserved and kinetic energy between initial and final states is conserved. Okay. So from linear momentum, what's the initial linear momentum of the system? Okay, it's not, we're not talking about just individual bodies right now. We're talking about the system m1 and m2 together. So linear momentum initial of m1 was m1 u1 plus of m2 was m2 u2. The final momentum is m1 v1 plus m2 v2. So we get one equation. Okay. Kinetic energy initial is equal to kinetic energy final. So from here we get half m1 u1 square plus half m2 u2 square should be equal to half m1 v1 square plus half m2 v2 square. Okay, we can simplify this as m1 u1 square plus m2 u2 square is equal to m1 v1 square plus m2 v2 square. Okay, on both these this is equation number 2. On both these equations, let's say we bring m1 terms to one side and m2 terms to other side. So this one becomes m1 u1 minus v1. This becomes m2 v2 minus u2. Here it becomes m1 u1 square minus v1 square equals m2 v2 square minus u2 square. Okay. This is equation 2, this is equation 1. Let's divide equation 2 by 1. What will happen? m1 will get cancelled, u1 minus v1, this one will be u1 plus v1. So u1 plus v1, similarly on the other side will be v2 plus u2. Okay. Let's bring u2 to this side. So u1 minus u2 is equal to v2 minus v1. This is a useful, very useful identity we get. So we have two equations, we combine those two equations and we get a third equation. Okay. This can be thought of as u1 minus u2 is what? u1 minus u2 is the velocity of approach or relative velocity of approach. Okay. And v2 minus v1 is what? Relative velocity of separation. Okay. So in elastic collisions or perfectly elastic collisions, because linear momentum and kinetic energy both are conserved, we arrive at a very useful relation here, that the relative velocity of approach is equal to the relative velocity of separation. So if u1 was, let us say, 4 meter per second and u2 was, let us say, 2 meter per second, then after collision, let us say this one was 1 kg, this one was 2 kg. Okay. After a perfectly elastic collision, what will happen? Let us say this is V1 and this is V2. Because relative velocity of approach was u1 minus u2, is 4 minus 2 is 2 meter per second. V2 minus V1, which is relative velocity of separation, will also be 2 meter per second. Okay. And then we can find out V1, V2 with the masses. So we'll come to that, but this is a very useful shortcut here. Okay. Okay. One thing to remember here, this is u1 minus 2, but separation is v2 minus 1. Okay. So don't make that mistake. There is a term I will introduce. It is called coefficient of restitution. It is represented by E. It is defined as velocity of separation by velocity of approach. So which is same as relative velocity after collision divided by relative velocity before collision. For perfectly elastic collisions, coefficient of restitution is 1. Okay. For inelastic collisions, coefficient of restitution will be 0, because in inelastic collisions V2 and V1 are same. So relative velocity of separation is 0. For anything in between, which is a partially elastic or partially inelastic collision, coefficient of restitution will be between 0 and 1. Okay. It can never be more than 1 though. Okay. Now let us look at some important observations from elastic collisions. So first off, momentum is conserved. So m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay. Second thing, kinetic energy is conserved, but when I use that equation with this one, we arrive at an important conclusion that velocity of approach, which is u1 minus u2, is equal to the velocity of separation v2 minus v1. Now from this we can write v2 is u1 minus u2 plus v1. Now if I replace v2 in this equation with this, we will get m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. v2 is u1 minus u2 plus v1. Okay. Now what we'll do is we'll bring all the v1 terms to one side and find an expression for v1 in terms of u1, u2, m1 and m2. That's our goal. Okay, so let's do that. Okay, so we get an important result here. We got V1 in terms of U1, U2 and M1, M2. So it's easy to remember actually. V1 is M1 minus M2 divided by M1 plus M2 times U1 plus 2 M2 divided by M1 plus M2 U2. Similarly, V2 will be M2 minus M1 divided by M1 plus M2 into U2 plus 2 M1 divided by M1 plus M2 U1. Okay. Okay. Now let's look at few special conditions or special cases. First case we will talk about is when M1 is equal to M2 is equal to M. Okay. So if you substitute M1 equals M2, this term becomes 0, this becomes 2M divided by 2M, so V1 becomes U2. So V1 becomes U2 and V2 becomes U1. Very interesting. So if both these had same mass, the velocities get interchanged. M1 was coming in with U1, it left with U2, and M2 was coming in with U2, it left with U1. Okay. Second case is if M1 is much greater than M2, okay, M1 is much greater than M2 and M2 is at rest, so U2 is 0, let's say. If M1 is much greater than M2, what will happen to V1? So we can write V1 equals M1 minus M2, which is almost equal to M1 because M2 is very less, and M1 plus M2 is also equal to M1 times U1 plus 2 M2. M2 is very less divided by very big is 0. So V1 becomes U1. Okay. So in this case, if M1 is a big mass, let's say like a truck, and M2 is a guy who is standing by the side of the road and it gets hit by the truck, there will be no change in velocity of the truck. It will continue with the same velocity it came in. What happens to V2? Now V2 is M2 minus M1. So M2 is negligible, minus M1 divided by M1 into U2, okay, plus 2 M1 divided by, so this term becomes 2 M1 by M1 or 2 U1. Now U2 is 0, so V2 becomes 2 U1. So the man who was standing there by the side of the road got hit by a truck, he will fly away with twice the velocity of the truck. Okay, important observation here. Number 3 observation or special case, M1 is much less than M2. So let's say this time M1 is a man on a bicycle, okay, and he is going and hitting a wall. Okay, the man on the bicycle is moving with some velocity u1, u2 is at rest, so m2 is at rest, the wall is at rest. What happens here? what will happen to the bicycle's velocity? So m1 is much less than m2. So this is, we can say, minus m2, denominator becomes m2 times u1, and u2 is at rest. So this is v1 becomes minus u1. What does that mean? So the man on the bicycle, he was coming with u1 velocity, hits a wall, he goes back with the same velocity in the opposite direction. Okay. What happens to v2? Anything happens to the wall? Let's find out. So m1 is, so u2 is 0, so this terms will be 0, and u1. So 2m1, m1 is very small, m2 is very big, so this will be 0. So there is no impact to the wall. Okay. So few special cases, I think it's worth mentioning, but in general, if you can remember these two, a lot of problems become easier. So in this case, v1, we can quickly find out. So v1 is m1 minus m2, so 1 minus 2 divided by m1 plus m2, 1 plus 2 times u1, which is 4, plus 2m2, so 2 times 2 divided by 1 plus 2 times 2. Okay. So this becomes minus 1 by 3, so minus 4 by 3, and this becomes 8 by 3, or this becomes 4 by 3. Okay. So v2 will become v1 plus 2, so 4 by 3 plus 2, so becomes 10 by 3. Now let's talk about perfectly inelastic collisions. Okay. So inelastic collisions. So let's say two masses m1 and m2 moving with u1 and u2 velocities respectively, u1 being greater than u2, head-on inelastic collision happens. So definition of inelastic collision is, after the collision, the two bodies, they stick to each other. Okay, and then they move with a same velocity v. So the separation or relative velocity of separation is 0. Okay. Now for inelastic collision, linear momentum is conserved, but kinetic energy is not conserved. So we will get the equation, initial linear momentum for m1 was m1 u1 plus for m2 was m2 u2 is equal to m1 plus m2 into v. Okay. So this is the only equation that is applicable for perfectly inelastic collisions. There is a loss of kinetic energy of the system. So K final is less than K initial. So we can, if we want, we can write half m1 plus m2 v square is less than half m1 u1 square plus half m2 u2 square. But remember, this is an inequality. Okay. Now finally, coefficient of restitution E, which is velocity of separation by velocity of approach. Now since velocity of separation is 0, coefficient of restitution for inelastic collisions is 0. One last topic to cover and we should be done with this chapter, and that is about elastic collisions, but not a head-on elastic collision, but where one body strikes another body, maybe not head on, but on the side. Okay, so let's say this is traveling with u1 m1 mass, and instead of hitting here, it hits here. Okay, this was initially traveling with velocity u2 m2 mass. So after collision, this is a not head-on or elastic collision. So how do the balls separate or bodies separate? Is one body goes in with velocity v1 so that it makes an angle theta 1 with the horizontal. The other body goes with velocity v2 so that it makes an angle theta 2 with the horizontal. Okay. So now in this case there are variables v1, v2, theta 1, theta 2, 4 variables, and we started with u1, u2, m1, m2. Okay. So let's see how many equations we can get. We ideally need 4 equations to uniquely solve all of these unknowns with this data that we started with. Okay. So first is conservation of linear momentum. Okay. Now in this case, because this is 2-dimensional collision, so the motion is not only in the x direction, but there is some motion in the y direction as well. So we can actually apply conservation of linear momentum in 2 directions. Okay. So in the x direction, initial momentum was m1 u1 plus m2 u2, and the final momentum in the x direction is m1 v1 cos theta 1 plus m2 v2 cos theta 2. Okay, so we get one equation here. Okay, in the y direction also momentum should be conserved. Now initially there was no motion in the y direction, so initial momentum will be 0. In the final, after collision, it is m1 v1 sin theta, which is in this direction, and m2's momentum is in the negative y direction, so it's minus m2 v2 sin theta 2, should be theta 1. So we get another equation. Okay. Now next thing we can apply is conservation of kinetic energy. Okay. Now kinetic energy is scalar quantity, so all we can write is half m1 u1 square plus half m2 u2 square is equals to half m1 v1 square plus half m2 v2 square. So we get a third equation. There is nothing else that we can apply. We had 4 variables but only 3 equations. So usually in these cases what will happen is one of these will be given to you. So either v1, v2 or theta 1, theta 2 will be given to you, and then you can apply these 3 equations to find the remaining 3 variables. Okay. So with that we will end this episode right here. We covered a lot. I purposefully did not do any numericals on this one because the numericals are pretty simple and straightforward, so you should be able to tackle them by yourself. But there is one special problem that I want to discuss a little bit in depth, so I'll make a different video for the same. But I will throw out the problem to you so you can try on your own. Look out for my next episode where I explain this problem in a little bit more detail. Okay, so here's the problem for you. So there is a body of mass ma traveling with velocity va, okay, on a frictionless surface. There is another body of mass b, okay, traveling with velocity vb. Now va is greater than vb. Again, this is no friction between the surface and mass b. So far it's simple, but now there is a spring that is attached to the end of mass b and it is uncompressed here. Okay? Question is, find the maximum compression of the spring the spring constant is given as k, and 2, the velocities after the collision is complete. Okay. So good luck with solving this problem on your own. If you are able to solve it, send me the answer in the comments and I'll be glad to respond back to you. Cheers.